Okay, so now at least this is recorded. Okay, so that's how you make the elliptic curve. And then you can do E dot gens. What this does is it will find P1 through PT, or literally die trying. In other words, it'll give up if it fails. Ooh, it found -1, 2. Hey. So I found the same point, and it is therefore claiming that this one point, -1, 2, notice there's a 3 tuple here. That's because the point is given in projective coordinates, just like I explained on Wednesday. Triples triples x, y, z modulo rescaling. And for every point except the point at infinity, the last coordinate will always be 1. So that's what's going on here. And now we can take, I'll call it P1, the first, which in Python is square bracket 0, element of the list V of generators. And now let's add that point to itself. Remember, that was the thing that we started over there, but I got lazy. So P1, actually I did it with minus P1, but boom! So we got something that has a 16 in the denominator, just like we anticipated from our calculation. Okay, and there it is, another point, which is supposed to satisfy the equation. Let's check to see if it does. So 113 over 16 cubed plus 6 times 113 over 16 plus 11. Is that or is that not equal to -1289 over 64 squared? Please, please. Yes. So as you can see, we've found a rational point. By the way, we can just keep doing that. Watch what happens. Nothing stops us from doing that. Whoa. Get another point. In fact, you can even do, you can type like a number like, I don't know, 17 times P1. That means add P1 to itself 17 times. Do you think, how big do you think that's going to be? Just a little bigger than the one we just saw? Massively bigger? What do you, any thoughts? What? Probably pretty big. Let's see. Boom, there it is. So this is just the x coordinate right there. So that is a rational solution to the equation y squared equals x cubed plus 6x plus 11. And moreover, it's a fact that every single rational solution to that equation you get by taking an integer times P1. Okay, I'm slightly lying, possibly. There's something called torsion, but I think this curve doesn't have any. Let me just check. If this number is 1, then what I just said is true. Yes, that number is 1. Okay, so what I just said is true. The set of points on that curve are exactly the ones you get by taking P1 and adding it to itself repeatedly, and also the negatives of those. And that gives you everything. So it's like, somehow it's like a dimension 1 vector space, that there's one parameter, you just take multiples of it, and it gives you everything. Except if you were to actually plot the multiples of this point on the graph, you would see that somehow the multiples of it would be dense inside of the points on the graph. Actually, let's see what the curve looks like. E dot plot. Okay, that's the picture. It was not like what I drew at all. This is what it looks like. But if you take the 1 point, -1, -2, these 2 points, if you take multiples of them, they'll get enormous, but they will also be dense in here, in that anywhere you look, if you look close enough, you'll see one of the multiples. You'll see infinitely many of the multiples, actually. It's pretty crazy. And that was just 17 times P1. I have to make let me make the screen small enough that you can see the whole thing. 17 isn't really that big. Okay, I should have a very small font there. So let's try, I don't know, 100 times P1. So it's starting to get bigger. Again, that's just a point on that curve that we found very quickly. So the points get very quickly very big in the sense of their complexity, the number of digits. And you never find this just by direct search, but there they are. But at this point, you know, it's somewhere in that picture, and if you draw all these points, eventually you'll get something that's dense in that picture. Okay? And you can repeat this process with, you can try to repeat this process with any curve, where you take the curve, define it, and then ask for the gens, the generators of the group. Gens gives you, there's a slight subtlety in that, I kind of want to ignore it, but probably shouldn't. I'll just say the word so I'm technically honest. this is the group that you get is an abelian group, and unlike what you have in linear algebra, there can be some. I'll just say it. So there can be some elements of finite order in that group. And when you call the gens command, it just gives you generators completely ignoring the elements of finite order. An element of finite order is one where you add it to itself and you get 0 eventually. So the point that we were just looking at, if you keep adding it to itself, it just gets bigger and bigger and bigger. But there's sometimes, rarely, but sometimes on an elliptic curve with sort of 0 probability, there can be a point so that when you add it to itself a few times, you end up getting back 0. You get the point at infinity. That can happen, and those are called torsion points. And I'm kind of ignoring them for what I'm doing. Okay, let's try one other curve, just to see what happens. Whoa. Okay. All right, somebody yell out an integer. 53. Okay, another integer. 21. Okay, here we are. E.gens. Again, I have no idea if this is just going to work instantly. Take forever. I don't know how many we'll find. There's exactly 1 again. That means, again, this curve has, like, the t is equal to 1. But notice this point's a little more complicated. But there it is. We can just you can do this. I'm kind of hoping to find one that has rank 2, where you have 2 independent generators. Okay, somebody yell a number at random. 47? Yes?
Is there a systematic way to find out all those generators? It seems like that's what they're doing.
There is a conjectural process that is supposed to find them, but there's no proof that it works.
Oh.
And because these are so small, it seems to be working.
So
However,
it may not work.
yeah, it turns out a lot of questions in number theory, surprisingly often, especially solving equations, you can contort them into a question about solutions to equations like this. And so you'll end up with, people will get a big list of elliptic curves that come from some process somewhere else in number theory, and then they'll say, hey, I like the generators. And if they're really small curves like this, it's easy, but it doesn't take long before it starts getting very hard. So like the first one, maybe it's easy, and then the next one they have 10 digits, and then they have 15 digits, 20 digits, and then it becomes impossibly hard. Even with a procedure we know will work, it still is very, very hard. Also, there are quite a few examples of curves where the coordinates are pretty small and the smallest solution is enormous. I can give you a striking example of this. Let's see. I think it's y squared equals x cubed. God, oh man. Can't quite remember. 7,000. Geez. I think it's that number. Unfortunately, I can't remember with absolute certainty what the number is, which is really annoying. I have to search around a little bit. There's a curve that's almost this. It's y squared equals x cubed minus, and then it's some number that's around 7,000. And it's called a Mordell curve, not the summer. It's just, anyways. Some people did an enormous calculation where for each curve of this form, y squared equals x cubed minus k, for k from 1 up to 10,000, they found generators for the group of rational points, except for one missing number where they couldn't do it. And so I decided to give that missing one as a Westinghouse science project to some girl from Guam who I'd never met. And needless to say, she unfortunately didn't solve it. She didn't find the solution. But she wrote up a lot of nice techniques for trying to find points on such curves. But another guy, Michael Stoll, about 10 years ago, did find the solution to almost this curve. Sorry, it's not quite that number. And it's enormous. Like if you write it out, it's just like really, really, really big. So, and it takes a lot of technique to find it. So it's probably one of the worst examples where the input is just 4 digits, and the output, that is the simplest point on this curve, is absolutely enormous. So that can happen. And in fact, is pretty much what you expect to happen with these. It's pretty annoying. So, actually, let me just, instead of making up kind of vague things about how elliptic curves come up and the numbers get big, I'll just check my email because there was a message like yesterday about this. MW rank on the list. This is very typical of what happens. So some random sounding person, Raymond Curdy, writes to the Sage list, I have some curves and I cannot compute the rank. That is, the number of independent generators. Help! So then they have their file full of curves, which the first one looks pretty doable, and then the numbers just start getting bigger and bigger and bigger. And here's the sort of responses you get. My response is, here's an example where I find the rank of the first curve in your list. And he's like, great, but it doesn't work on anything else, because they just keep getting bigger and bigger. And then somebody else points out that it's really hard, and sorry, etc. And that there was a bug in Sage. So, but that's pretty typical. That people are doing something else, they run into a bunch of elliptic curves, they want to find the rational points in those curves for some reason, and they get stuck because the numbers get very big. In any case, I'd really like to find one with 2 independent points on it, and I don't really want to cheat, but I will. There's another way to give curves by a name, which is, here's my favorite curve, 389A, which if you ever see my car, the license plate is Sage 389, and that's because of this curve. Here's what it looks like. I know that's not y squared equals a cubic, but you can do the following, E dot short Weierstrass model, and that'll give you back. All that does is complete the square and so on. Okay, so it's y squared equals x cubed minus 3024x plus 46224. Okay, so it's that curve. I'll just reassign it, and so it's this curve. And now if I do E dot gens, look what happens. Boom, 2 independent points. So now for this particular curve, in order to describe the collection of all solutions, you have to take some number of copies of the first point and add that to some number of copies of the second point, possibly negative numbers, okay? And that will systematically give you all the points in this curve. And this is, by the way, the simplest curve where 2 points are needed, or just 1 isn't enough, in a certain sense. I haven't defined simplest, but there's a notion of simple, where this is the simplest one. And there are major unsolved problems just about this particular curve, just this one curve itself. Okay, so we got time, 4 minutes. Okay, so let's see. I don't have enough time to talk about Diffie-Hellman, but I do have enough time to show you a couple more examples of the group on an elliptic curve. And in preparation mentally, I'm going to show you an example of our finite field. Okay, so let me make this big. I'll skip this elliptic curve over Q example because it's like exactly what we just did. Now we'll talk about an elliptic curve modulo P. Okay, so everything we've done so far, it's all been about elliptic curves and other curves and rational solutions. However, just think about it. This group operation right here, let's suppose you handed this to your engineer friend and you said, hey, implement this in Perl or whatever, I don't know. Some funny language, and they might think, oh, I don't want to work with rational numbers. I don't have a rational number library, so I don't have to work with fractions. They'll overflow and stuff, and it's really horrible. So you tell them just reduce everything mod p at every step. Do all the arithmetic as given, but work modulo p. It would work. It makes perfect sense. Numbers mod p, you can divide them, you can add them, etc. And in fact, you could just take all the points modulo p on an elliptic curve, and then do addition and multiplication and so on, and get a group operation. So, oh, and again, it should not be obvious to you that you get a group from this construction. That's a deep and difficult thing to prove. Okay, so here's a curve. Y squared equals x cubed plus x plus 54 modulo the not so big prime 59. Okay, so let's define it. Boom. And I can plot it, actually. It kind of looks less nice than the plots of elliptic curves over Q, because, I mean, it's just a set of solutions to this equation up there, modulo 59. So when I'm drawing this, I'm just putting the x and y coordinate mod 59. I put a dot at each point that solves the equation. It should just look like a bunch of random points. That's all it is. They're not going to be like arranged in a nice loop or something, because modulo 59. Does that make sense? So like if you take a dot here and then plug it into the equation, it doesn't satisfy it at all unless you reduce mod 59, and then it does. You get a congruence mod 59. Okay, so that's the group. The group is this set of blue points plus one point in infinity. And given any 2 points here, there's a natural way of adding them together, namely by the algorithm that I have behind here on the whiteboard. Okay? And in practice, what happens? So there's 57 points total. And let's just do an actual addition. So here we are. I just chose 2 points. 4, 2. That satisfies the equation mod 59. 519 does as well. And using p plus q, I get the sum. And it's 4426. So there's no fraction, there's no denominators at all because we're working mod 59. There you are. Now, if we were to do this, instead of working mod 59, mod a large prime, then we might imagine constructing something like the Diffie-Hellman key exchange, where we take our point and multiply it by some big random number, and the other person would multiply it by some big random number, and then we would each multiply by we would each multiply the other person's thing by that same random number, and we would get a shared secret, where the shared secret, instead of being a number, is a point on the curve. But there's a major subtlety to doing that, which turns out to require some deep stuff from modular forms, which I'll tell you about next time. Okay, so on Monday we'll talk about Diffie-Hellman on an elliptic curve.
Oh, yeah.